Hello everyone, I'm Lei Gao, a PhD student from University College London. Today I would like to present our paper StableLev, Data-Driven Stability Enhancement for Multiparticle Acoustic Levitation. My co-authors are Giorgos, Christopoulos, Prateek, Mittal, Ryuji, Hirayama, and Sriram Subramanian. We are here talking about the acoustic levitation, which allows for the levitation of objects through ultrasonic standing waves by computing and optimizing sound propagation, and phase array transducers reshape the sound field to dynamically trap objects at different locations in the mid-air. Such technical advances make acoustic levitation a versatile interface applied in various application scenarios in the HCI community. It has been actively used for physical interaction with mid-air content in 3D space, and levitated objects can also render volumetric displays and facilitate data physicalization. More promising scenarios including contactless assembling, object delivery, and even for fabrication. However, we have noted some technical challenges. Stability issues have seriously hindered the dynamic interaction, animation, and mid-air manipulation. The system's robustness is not reliable in real scenarios, and more particles and complex content lead to higher failure rates. We also experienced such failures in our test, where particles dropped accidentally, preventing the successful completion of motions. This caused a discrepancy between theoretical simulation and practical tests. Instability issues are firstly getting attention from the physical domain, but people are mostly focusing on single-axis levitation and observing the oscillation phenomenon, while HCI researchers concerned about the displacement between the real and target positions of single traps. The dynamic multi-point levitation still faces significant stability challenges that prevent its reliable implementation in real applications. So to characterize such unpredictable and unexplainable phenomenon, we seek to foster rigorous analysis and algorithm development based on a historical dataset. However, we realize that the missing key in this domain is the absence of a dedicated dataset. For the first step, as we noticed such instability issues in our real experiment, we decide to create the hybrid levitation dataset with both simulation feature and experimental features to describe the dynamic levitation process. We use the path planning algorithm to generate various feasible motion trajectories for multiple particles. Based on those trajectories, we compute the analytical features like the trap position's intensity and acoustic point parameters like amplitude and phase. We also observe the levitation system running the same trajectories and record the real experimental features like real positions and real trajectory outcomes. All those time series features constitute our final hybrid levitation dataset. It is worth noting that levitation solvers play a crucial role in shaping the sound field and generating the levitation traps. We selected two representative solvers, naive and GSPAT. They both estimate the phase at the trap point and compute the phase of transducers using backward propagation. The naive algorithm assumes all points share the same phase, while GSPAT iteratively optimizes the estimated point phases. Among our analytical features, we examine their correlation, and we find that amplitude is strongly correlated with Giorgos potential and stiffness. Also, point phase changes has a relatively high correlation with the average transducer phases changes. To make these features the same dimension and with less computational cost, we selected focal point amplitude and point phase change as analytical features. For experimental features, we use the trajectory outcome, stable or unstable, as a feature label. To find the unstable sections or anomaly parts of levitation trajectories, we use AutoEncoder-based deep neural networks, which are capable of identifying anomalies from complex datasets. The working idea is to input the features of normal sequence to the encoder and decoder, and the output has the same dimension as the input. so the autoencoder could learn the pattern of normal sequence. Next time, when we input an abnormal sequence, we compare the reconstruction error between the input and output. And once the error is beyond the threshold, we detect the abnormal time steps. We selected 3 different deep learning models based on AutoEncoder, which are adept at reconstructing time series data and detecting anomalies. The threshold is a critical parameter, and we find that the thresholds with 92% make the model achieve the highest performance. And for more detailed model parameters, please refer to our paper. Here are some anomaly parts that are found in the trajectories rendered by the red dashed lines. At the same time, we also align the time steps with real particle position displacements. For the particle 6, the anomalous regions just appear before the real drop happening. Similarly, in another group, our model suggests that anomaly regions appear before the particle force drop, and these findings prove that our model captured the meaningful anomalies. After detecting anomalies, we aim to correct these anomaly steps and fix the dropping situations. Here, we propose an amplitude amendment strategy, which involves slightly increasing the amplitude of unstable particles, or both increasing and decreasing the amplitude of a few particles. Like the dropping particle 2, which moves along the green dashed trajectories, could be fixed by tuning the amplitude at anomaly regions. We demonstrate the anomaly amendment in our real experiment. Before the amendment, only moving along the planned trajectory, one particle suddenly dropped and failed to reach the target positions. Well, after applying the amplitude amendment strategy, we successfully completed the motion trajectory without any failures. So in summary, we built and open-sourced the first hybrid levitation dataset, and we propose a StableLev pipeline, which uses effective features for stability prediction and enhancement. At the first attempt, we recognized some limitations in our model and training performance. However, we hope that in the future, more researchers can build upon our dataset and address emerging challenges using machine learning or deep learning methods in this domain. Thank you for your listening. Please feel free to reach out for more discussions.